The Bohr Model. Properties of the atomic model that predated the Bohr model. An atom is composed of a very small positively charged nucleus, which contains neutrons and protons, and even smaller negatively charged electrons outside the nucleus. The electrons and nucleus are attracted to each other since they have opposite charges, and the electrons are free to move in the almost empty space of the atom. Since atoms are almost completely empty, there's nothing to keep the electrons and the nucleus apart. And the electrons and protons are opposite charges, so they should attract. Classical physics could not explain how this atom could exist. Perhaps the electrons orbit the nucleus, like planets orbit the sun. However, if this were true, electrons would constantly be accelerating as they orbit around the nucleus. Right? Their direction of velocity keeps changing. An accelerating charge radiates energy in the form of light. Atoms would constantly be emitting light. A charge radiating light, here it's radiating light, loses energy according to the electromagnetic theory. All the kinetic energy of the electron would be radiated away in about a billionth of a second. The electron would fall into the nucleus. All the atoms in the universe would collapse. And here's the death spiral of the electron. Problem number 1 with this atomic model. Atoms are stable, they don't collapse. If an atom's electrons were continuously orbiting the nucleus, they would radiate energy and collapse in a billionth of a second. This is not observed. Otherwise, we wouldn't be here to discuss this. Problem 2. Atoms do not emit light most of the time. If an atom's electrons were continuously orbiting the nucleus, they would radiate light continuously. This also is not observed. Problem number 3. When atoms do emit energy, it consists of only specific colors. Most colors are absent. Only narrow lines of color are observed. This is the example of a continuous spectrum, but what we really have, and here's a hydrogen spectrum, you only have a few very narrow, colorful lines. That is not a continuous spectrum. Niels Bohr interpreted these observations and created a new model. Notice, the observations were not changed. You needed a new model. And this new model of the atom explained the existence of the emission spectra, the different colored light coming out, and provided a framework for where the electrons can exist around the nucleus. Bohr then proposed that this pesky little n here, it defined permitted, notice it's in quotes, permitted electron orbits around the nucleus. So electrons could orbit the nucleus just like the planets orbit the sun, but only at permitted radii. For example, you've got this first orbit here, n equals 1. So that's an electron orbit. Here's the question, why can't we see the nucleus? Well, that's really incredibly tiny, way, way smaller than that little dot. So when you look at these circles, those are electron orbits. These radii increase in proportion to n squared, which is the same n squared that the 3 scientists came up with, Pasch and Lyman. And the orbits get much, much larger as n increases. So you can see how n equals 4. See the gap between 3 and 4? That's greater than the gap between 3 and 2 and between 2 and 1. Bohr's model did not allow for electrons to exist here. They had to be in this blue orbit, this green, this red, and again the colors are just to help us look at them, and in here. You could not find an electron here, for example, or an electron here. And he said that when they were in these orbits, they would not radiate energy. That's kind of a problem because that violates the rules of electromagnetism, since orbiting charges should radiate energy. But Bohr said somehow these rules don't apply to electrons in these orbits. Bohr then postulated that electrons would radiate or absorb energy when they moved between the permitted orbitals. So you could go from n equals 1 to n equals 2. Never really said how they would get there because the electrons weren't allowed here in the space between the orbitals. And we have each orbital representing a different energy level. The energy of the light emitted, that's when you lose energy, or absorbed, when the electrons gain energy, is equal to the difference in the starting and ending energy level of the electron. So let's just say what that's talking about here. Here's Balmer's equation. And you can see we have a subtraction here, right? We have this n, which is the number of your orbital, and then we have this 2. So it looks like we have electrons moving between an n equals, well, here, 3, 4, etc. level, and the 2 level, right? Here's n equals 2, here's n equals 3, and n equals 4. Because we know that energy is proportional to 1 over the wavelength. So this theory here is based on this formula that came up from Balmer.
But what are the energy levels? For each n, again, n, just integers 1, 2, 3, etc. There is an energy level designated E sub n. The ground state of an atom is its lowest energy level, where n is equal to 1, and we will call that E sub 1. Then E sub 2 will be the next energy level. That's when n is equal to 2. Bohr showed that the energy of an energy level, E sub n, is equal to E1, right? That's the lowest energy level, divided by n squared. So the energy of the second energy level, E2, is found by plugging n equal 2 into the equation and finding out that the energy level, E sub 2, is equal to E sub 1 divided by 4.